Alright folks, welcome back to the channel. So let's jump into another problem, and today's video we have the 13th question of the first chapter of the Beer and Johnston textbook, and we have this aircraft tow bar which is positioned by means of a single hydraulic cylinder. So this is the tow bar that we are talking about in the first part. So aircraft tow bar by means of a single hydraulic cylinder. That's the hydraulic cylinder by a 25mm diameter steel rod. So we know the diameter of the DC and the rod in that hydraulic cylinder. So by a 25mm diameter steel rod and by the two identical arm and wheel units DEF, we're talking about this unit in here, and we know the mass of the entire tow bar, which is again what we have in here, is 200 kilograms. So we can find the weight easy enough. Our weight will be mass times acceleration of gravity, and we also have the location of the centroid or center of gravity, which is G in this figure. It's going to clean up, you can see the G, and for the position shown we need to determine the normal stress in the rod. So at the end of this question we have to find the normal stress at member DC, and again we have the information about the diameter of the DC, which is 25mm, and the other information that we have is the mass, and we know that it's applying at point G, so it's easy enough to find the weight, mass times acceleration of gravity on Earth, 9.81 meter per square second, and if we calculate this we're gonna get 9962 Newton. So obviously we are in equilibrium and we can use our equilibrium equations. So let's start with the free body diagram of the entire system, other than the wheels that is attached at point A. So we have the whole thing. This is our tow bar, this is the member DE, and we have this wheel in here, and this is our member DC, and we are interested in all the external forces in here, which is the force at A. We have a pin, we have to consider both X and Y component. We have a normal force at the wheel at point F, let's call it R, and at point G we have the weight of this tow bar, and that's pretty much all the forces that we have in here. And what we are interested in here is the normal force R, because after that we can move on to the free body diagram of member DEF, and from there we can find the normal stress at member DC. So here, if we do the moment about point A, counterclockwise positive as always, we can get rid of all the unknowns other than R, and all the dimensions are known in here. We have the moment of force R, which if we look at it, it's a counterclockwise moment, so positive R times the distance from a line of action of R to F, which is what we have in here, 850mm. We don't need to do any unit conversion because it will be cancelled out. And we have the moment of the weight, which is clockwise, so we have a negative sign, and the distance would be the distance from G to A, which is 1150. And since we are in equilibrium, this will be equal to 0, and we can find R in here, which will be 2654.5 newtons. So after this we're gonna move to the free body diagram of member DCF. So this member here, DCF, and this will be something like this in here. So we have some unknown at E, we can call it EX, EY. We have our wheel in here and the normal force R, and we have the force at the hydraulic cylinder, which is what we are interested in, because at the end we are looking for the normal stress in the DC, which would be basically force over the area of the cross section. So as long as we have the force, we can find the final answers. So let's just consider the force in this direction for now, and at the end if we get a negative sign, it's gonna show that our assumption wasn't correct here. So we can find this angle easy here. It's angle theta, which is the angle with the horizontal in here, and we have all the dimensions. We know that if we look at this right triangle here, the tangent of theta would be the opposite, which is 100 over 675. So we can find the theta easy, 100 over 675, and from here theta would be the tangent inverse of 100 over 675, and the theta will be 8.42 degrees. So same thing, we are in equilibrium, we have the most unknowns at E. If we do the moment about point E, we're going to get rid of all the unknowns at point E since they won't make any moment. We already know what the R is, and the rest of this is pretty easy. We only have to do the 2D shortcut that we have for finding the moment. I'm going to put the link in the description below if you guys need to refresh your mind. I have a different channel that I cover all these concepts of moment and the engineering mechanics course. So feel free to check it out if you need to refresh your mind. And so here we have the moment of X and Y component of FDC, which we can show it like that. And as we can see, the vertical component won't make any moment because it passes through the point E, and we only have the moment of the horizontal component, which will be a clockwise moment. So minus FDC cosine of theta would be our horizontal, and we are interested in this distance. And if I look at here, we see that I'm gonna clean up the figure, we can see it better. So we are interested in D to E. We know we have 450 here plus 100 here, so 550 would be our. So this will be 550 millimeter. All the dimensions are in millimeter as we can see in the figure. And we also have the moment of R, and the distance that we have for R again is 500. So we can see that the moment of R is also about point E clockwise. So that's going to be -2 R times 500 is equal to 0. We already know theta, we already know R, and we can find FDC in here. So basically our FDC will be minus 500 times our R, which is 2654.5 divided by 550 times cosine of 8.42 degrees. And if we calculate this, we're going to get minus 2439.5 newtons, and we should be able to find the normal stress at rod DC, which will be basically FDC over the area of DC. The area is pretty easy. We already have the diameter. It will be pi over 4 times the diameter would be 25 millimeter squared. So that's going to give us the area, and in order to get it in meter, we're going to do 10 to the minus 6 to get it in meter squared. And here we have minus 2439.5 over pi over 4, 25 squared times 10 to the minus 6, and we have Newton per meter square, and the final answer will be in Pascal, which will be minus 4 times 97 times 10 to the 6 Pascal. And if we want to write it down in megapascal unit, it will be minus 4.97 megapascal, which would be the final answer for this question. So yeah, that wraps it up for today's video. If you guys have any question, feel free to drop it in the comment. I'd be happy to answer those. And you guys take care. I'll see you in the next one.